So let's welcome our third speaker for this session. So we like to keep a tight ship here so it's a pleasure to have Alexander Stottmeister talking to us about embezzlement of entanglement and the classification of on-model algebras.
Well, thanks, and well, first of all, thanks to the organizers for inviting me to present this work here, which was a joint effort with these three people you see here, Henrik Würming, Laurens van Leijk, who is also here, and Reinhard Werner. And what I'm talking about will be based on these works which are listed there. So let me start with what is actually embezzlement of entanglement. Yeah? So according to the next version of the Cambridge Dictionary, it's the crime of secretly taking entanglement that is in your care or belongs to an organization or business you work for. So now, well, let me explain what I mean by this, but before I want to illustrate how to think about this. Yeah. So instead of embezzling entanglement, I want to talk about the embezzlement of chocolate. And here maybe you know this cartoon. So we split our resource apart, move the pieces around, reshuffle them, and end up with a free bit in the end. Yeah, so. But of course here, I mean, this is only a sketch of the whole thing. And the important thing is that for this definition I gave before, here this embezzlement of chocolate is very easy to detect. Yeah? So you can just measure the amount of resource you had in the beginning and in the end, and then there's an additional piece. So somehow that cannot be the case. And in the quantum setting, what we want to do is we want to actually do it secretly. And the setup will be as follows. So we have Alice and Rob, which have a local quantum system, finite dimensional, which is represented by these kind of quantum laptops they have. Yeah? And they share a resource system. And typically in quantum information, this resource system would be kind of a state in a tensor product that is coupled, tensor product space that is coupled to these local systems. And well, then the important point will be that we want to do something secretly. And secret here means that we want to do this so that no record of crime exists, of our embezzlement of entanglement. And this means here that we don't want to use classical communication. So we only allow for locally operating on the parts of the Hilbert spaces of the resource and their local quantum systems. Yeah? And so what we want ideally to hold is that we have our resource state, this omega, in this joint Hilbert space of the resource system. And then we have some initially unentangled state of the local systems. And we would like to operate with local unitaries, which are referring to resource part of Alice and the resource part of Bob, as well as their local systems, and get out the original resource state together with now the transformed state, transforming the original initial product state into an arbitrary entangled state on the local systems. And of course, we know also in infinite dimensions from the work of Richard Cleave and Paulson that this is impossible, but with every good local result there comes the question of how can we circumvent it if we slightly change the goalposts. Yeah? And this was observed in the following sense that by Van Dam and Hayden already 20 years ago, that if you allow for small errors in this context, you can actually get away with embezzling entanglement in this way in the following sense. So they proposed a family of states, which looks pretty simple. Yeah? So this type of state for the resource. But now you have, instead of a single state, you have a family of resources depending on this resource dimension S. And they fulfill this property that if you allow for some small error here, depending on basically the Schmidt rank of the entangled state you want to embezzle and the size of your system, then you can make the error when comparing the original product state and the resource to the target state and the resource arbitrarily small. And that's what one usually calls an embezzling family. And there has been some follow-up on work on this, and they have already shown that essentially the error you get here is optimal due to the Furness-Audenard inequality. And there were some further works that have argued that this kind of family is also unique in the sense that the Schmidt values of the spectrum of this resource state have to have this asymptotic scaling of 1 over j. So here the Schmidt values would be the squares of the coefficients on each resource state. So, and well, now what we wanted to do in our work is basically ask whether you can also find an idealized resource, of which this family of systems is a limit. So we want to find a single state on some quantum system that already has this property, which is shown here, but without varying the dimension n. And well, of course, you cannot just simply take the limit of this family, because that has a divergent prefactor, so that doesn't really make sense. So how would you go about with this? And well, for the rest of the talk, I want, in addition to pose, well, complemented by this initial question, two other questions, which is first, as I said, are there quantum states that can embezzle states of arbitrary Schmidt rank to arbitrary precision, so arbitrary d in this previous equation, and arbitrary error? And if you can find something, then we will call it an embezzling state. And the second question would be, are there quantum systems where every state you pick on this system actually has its property? Sounds a bit weird because already the initial question is a bit strange. And then third question, well, do they, at least in some idealized form, even exist in nature? And well, I want to convince you that basically this is all true in some sense, which I want to make precise. Okay, so, but since we have seen that this question of embezzlement, of entanglement does not really work well in the tensor product framework, we will actually move to the commuting operator framework. And this means, so just to briefly recall it, in the setting that instead of the resource Hilbert space being tensor product Hilbert space, we just choose a joint Hilbert space for Alice and Bob in which they can act locally independently in the sense that they have access to operator algebras, specifically for Neumann algebras here, which are commuting on this joint Hilbert space. We will assume that the algebras, they have access to our factors, so there are no classical degrees of freedom around. And for technical reasons, we also have to assume that they are Haag dual in the sense that one is the commutant of the other. So Alice has like the maximal amount of operations compatible with Bob's operations. Okay, and well, then in this setting, we define bipartite systems and embezzling states in the following sense. So a bipartite system is just a triple. Now this always refers not to the full situation, but just the resource. So think of this H as the resource space. And then locally, we also couple like finite dimensional tensor product for the local systems of Alice and Bob. So this consists of a von Neumann algebra and its commutant, and an embezzling state in this resource system is a state such that if you take any finite dimensionally entangled, possibly entangled state, and any error epsilon, then you can find local unitaries which not only act on the, which are unitaries in this M for Alice, and also acting on the local resource or on the local Cn, and such that you can make this error up, that you can achieve this error for the targeted state. Okay, and now we know from other ideas in quantum information theory that it's typically a good thing to, if you want to understand these bipartite entanglement properties, then that you should pass, or that you might want to pass from the bipartite setting to the monopartite setting. So instead of talking about the joint resources and the entangled states on that, we want to go to the marginals for the local systems of Alice and Bob. And for pure state entanglement theory in the tensor product setting or in the semi-finite setting, we know that there's something called Nielsen's theorem, which links the entanglement properties of a bipartite pure state to the majorization theory of the reduced state, where we either reduce to Alice or to Bob's subsystem. And the link is essentially provided by purification. And okay, and to do this, we also need the concept of a monopartite embezzling state in our setting, which is basically now the same statement where we just talk about the marginals of, let's say, Alice. So we take what was before this capital omega state, the resource state, we take the local marginal on Alice's side, which is now small omega, and then again we ask for any error and any now possibly mixed state on the local subsystem of Alice, that we find a unitary such that we can minimize this error, or that we can achieve this error. And for technical reason, which is related to this question of Haack duality, we want that our system is a standard bipartite system, which means that M should be in standard form. I mean, we can prove the result we have also without assuming this from the beginning, but that just makes life a bit more complicated. Yeah? So it's easier to assume. In a sense, in the end, you also see that M will be necessarily hidden in standard form. And okay, now the first result is that essentially by purification, yeah, so on a bipartite system, entanglement of embezzlement in the bipartite world is the same as in the monopartite setting, essentially, because if you choose the unitaries for Alice locally in the monopartite setting, then you can, in the standard, if your system is a standard bipartite system, you can use the modular conjugation to get the corresponding objects for Bob. So you have some variance in the error, something like square root 2 appearing there. Okay, and now to actually understand when this property of embezzlement can happen, we introduce also something to quantify embezzlement. So in a sense, we want a quantitative version of this error statement. This is maybe on the first side a bit daunting quantity. So we have here essentially this error term, which was relevant in the or which we use to define what it means to have embezzlement. Yeah? So if you have an embezzling state, omega, monopartite embezzling state, then this infimum here would be 0. But you can, of course, also define this quantity for any state on the von Neumann algebra, and its maximal value will be 2. And well, and this quantity we looked at for a specific choice of error and a specific choice of input state, and then we take the supremum over all possible states we want to embezzle in all possible dimensions. Yeah, consider this quantity we call kappa. And now we want to see what kappa can actually be. Yeah, so for the moment we only know it's at most 2, and maybe if there's some embezzling state somewhere, then it will be 0. Okay. And go even a bit further, we introduce a best worst case error and a worst case error, where we also optimize over the state spaces on algebras. And then basically by definition, K-min and K-max will be algebraic invariant of them. And of course we can ask, what are they? Could be the same, won't be the same. Okay, and now to understand the result, let me just briefly recall the various types of factors we can have. So there are the 3 types, which are further distinguished into subtypes, and well, type 1 is what we see, what we get if we think about matrix algebras, essentially. So finite dimensional matrix algebras, or in general B of H, for H some separable Hilbert space with dimension n. Then we have in the type 2 case, which is not so relevant for this talk, but will be probably mentioned in Lauert's talk, the subtypes 2, 1 and 2 infinity, and then for type 3 we have a continuum. Possible subtypes, for every lambda in 0, 1 we get a subtype, and these are specifically distinguished by the first 2 types being semi-finite, in the sense that they have a natural trace on them, which is non-trivial, and in the type 3 case we have purely infinite von Neumann algebras, and which don't have a trace, or non-trivial trace. Okay, and now our main result is the following. So you can actually compute these invariants kappa min and kappa max, and you see that in the semi-finite case there cannot be any embezzling states. Because this kappa min, that would be 0 if you had an embezzling state. But it also takes the maximal value. But what's interesting is that, well, maybe we first look at the middle column for type 3. If you're in the case where lambda is strictly between 0 and 1, and there will be some embezzling states, because this kappa min is 0, and it's actually, you can also show that it's attained by a certain state. And well, I will come to that later, but you also find this for the kappa max, you find this interesting number, some of you might recognize it. And now we also get an answer to our third question. So in the type 3(1) case, we get also that the kappa max is 0. So actually for these types, every state is embezzling. Every normal state on that von Neumann algebra is embezzling. And in the type 3(0) case, the situation is a bit more complicated, but also interestingly, you can only get like 2 possible values for type 3(0) for the kappa min. So either there is an embezzling state, then it will be 0, or it fails in the most significant way, if you want. So then it's more like the type of the semi-finite case. So you can only get either 2 or 0. And well, this basically follows by work of these authors here. So Amin actually informed us about this. So due to his work, we were able to complete this table before. We only knew that there are some cases where it's 2 and it's 0, but there could have been some intermediate values, but apparently there's a strict dichotomy for this. And well, it essentially follows from some ergodic theory, which I will come to in a moment. Okay, and now the nice thing here is that if you ignore the semi-finite case, you actually, from this quantity that measures how well you do at embezzlement, you recover the con-classification of factors, or the subtype within this classification. And this number here, which you get here, that's actually the radius of the state space. If you
is it actually obvious that it should depend only on the type?
Yes. I mean, it's not clear that you get a function that is 1-to-1 for lambda.
No, but you could have different factors of the same type. And so is there any reason why it should depend on the type?
Well, you will see from how we prove this that it's essentially because when you might know that this is the state space radius for the type 3 lambda factors, and in a sense, once you reinterpret this quantifier kappa in terms of the modular flow, you see that it is directly linked to the computation of the distance of unitary orbit. Well, and this brings me back. Yes.
It's a bit disappointing that the properties of the Neumann algebras don't go in.
Yeah, maybe in the multipartite case.
Amenability.
Maybe in the multipartite case you can get something more. So that we don't know yet. But in the monopartite case, it's just this. In the bipartite case, it's only this. Well, okay, as I said before, so how we prove this is basically by going from the bipartite setting to the monopartite setting. And in a sense, we want to have something like the analog of Nielsen's theorem for stating something about the marginal of our resource state on the local algebra of L, let's say. And how do we do this? But the main idea here is that we use the flow of weights, but with a slight additional ingredient, in the sense that we learned from these works by Kohn, Takesaki, and also later Agerup and Störmer, that when you start from a von Neumann algebra together with a normal state, then you can of course pass to the flow of weights, which is this idea of like forming the cross product with respect to the modular flow of some semi-finite faithful weight, and you take the center of the resulting semi-finite type 2 factor. But there's also a construction which takes along the state and which gives you a probability measure on the flow of weights. And this is basically presented in this work here. So what you do there is that you get this flow of weights in the sense that you, as I said, you form this cross product, you look at the dual action to the modular flow of some semi-finite faithful weight, and then you take the dual weight given for a given state, and you restrict it in this sense to the flow of weights. So you do a certain cut basically cut the density matrix, if you want, for this dual weight. That actually gives you a state on the flow of weights. And then the observation is that embezzlement on this side is actually nothing but the invariance of the probability measure under the flow of weights. So that's the important observation. And you can even quantify this in the following, using the following tools. So Agrup and Störmer, they showed that if you want to compute the distance of unitary orbits, then that's actually nothing but the distance of the probability measures on the flow of weights, and not in the natural total variation distance of this probability measures. And now our main result of the paper, we analyze this, is essentially that this kappa is nothing but this quantity. So you look at the maximal distance you can achieve by shifting the probability measure along the dual action on the center, comparing it to itself. So that's so in this sense, embezzlement is not only equivalent to invariance, but it's even equivalent in a quantitative sense. That's the important thing, and then you can compute this quantity in certain cases. Actually, for the type 3 lambda case, you find if you construct it in the hyperfinite setting, for example, with the power state, then you find that the power state is exactly the one that maximizes this. What's not so clear to us, or we don't know how the embezzling state in that case actually looks like. I mean, we know the spectrum, of course, so you can write down the spectral distribution. But it would be nice to have a natural candidate for the actual state. Okay, and well, just as an illustration, with the flow of weights for these type 3 lambda factors can be visualized like a circle like this, where the flow is essentially the rotation around here, and the statement that you have an invariant state just means that you can find an invariant measure, which is here just a constant measure. So in this sense, it's known which, let's say that the unitary orbit of the embezzling state is clear in that case. And also, I think this picture makes very clear why you have universal embezzlement for the type 3-1 factor, because you just have a degenerate spectrum, so everything is invariant there. Okay, just to recall the main result. So we have this computation of the kappa min and kappa max values. Now let me talk a bit more about universal embezzlement. So I promised you that there's some kind of interpretation where you can, or there are some models where you can find this actually in physically or literally reasonable systems. But first of all, I want to also show you another way how to understand this correspondence between universal embezzlement and type 3-1 factors. So that type 3-1 factors are actually universal embezzling, you can basically guess from the outset, because if you know about this, if you know this result by Kohn and Störmer about the homogeneity of the state space, and you realize that type 3-1 factors are properly infinite, then of course the embezzling property, or the universal embezzling property for type 3-1 factors immediately follows. The other way is the slightly more difficult one, but then we have also shown in our paper that if you have an embezzling state, this automatically implies that the modular spectrum has to be R plus in that case. So which means that you necessarily get a type 3-1 algebra. Okay. Now, where can we find these type 3-1 factors in, say, statistical mechanics and relativistic quantum field theory? Well, in statistical mechanics, for example, we can find them in infinite spin chains and also critical fermion systems. And here the idea is that bipartite situation corresponds to the setting where you have this infinite chain, you split it in half, give one half to Alice, one half to Bob. That's the resource state. And now, which kind of natural states produce type 3-1 factors here? Well, a very simple example would be the transverse field XY chain. So you just have basically a simple magnetic model of interacting spins, and if this magnetic field strength here is not too strong, these are automatically critical systems. And then the statement would be that if you take the ground state of this Hamiltonian, in the sense that you look at the automorphism group generated by this thing on the infinite spin chain and then ask for the ground state with respect to this automorphism group, then in the GNS representation, the weak closures of the left and right half-chain algebras are type 1. And in this sense, this ground state, or in that case, even every normal state in this in the sector or in the folium of the ground state will be an embezzling state. And more generally, what we have also shown is that if you take any critical translation invariant free fermionic chain, or its dual spin chain where the Jordan-Wigner transformation, then you also have actuality and this type 3-1 property. And I don't know, maybe some of you know, but in the case of gapped systems, so away from criticality, there are results of Matsui which say that in that case you always get type 1. So there seems to be a dichotomy, since that either you have a gap, you get type 1, or it's critical, and then you get the type 3-1 case. And would be an interesting problem whether you also can get type 2 in that case. Yeah? I mean, you can't get type 2-1 in the translation invariant setting because that basically forbids that you have a trace, or a tracial state, I should say. But type 2 infinity could even be possible. We don't know. And now, well,
these are all hyperfinite.
These are all hyperfinite in that case.
It's just one type 3-1 factor.
Yes. But the result about, I mean, the statement of using the flow of weights shows it for beyond the type 3-1 case. Okay, now one thing I left open, or which I didn't really comment on, is this question of what's the actual link between these embezzling families and the embezzling states. Yeah? So we just ask whether there are these idealized resource states, but there is some interesting link. So if you think about von Neumann algebra, or if you take a model where the von Neumann algebra is actually hyperfinite, then you can show that if you have an embezzling state on the von Neumann algebra, you restrict it to the increasing sequence of matrix algebras generating this von Neumann algebra, then that will actually be I mean, these restricted states will be an embezzling family in the sense of Van Dam and Hayden. So, and actually, in that case, these families have a slightly stronger property in the sense that the unitaries you can choose from the embezzling state, they are consistent in a sense. Yeah? If you take the restrictions and then take an approximation of these unitaries along the increasing sequence of matrix algebras, then you don't have to re-choose these unitaries all the time. Yeah? But in this example by Van Dam and Hayden, you don't have this property. So in this sense, the families you get from embezzling states have slightly stronger properties, and that's what we call consistent, in the sense that the unitaries you choose for these families are consistent. But then, assuming this kind of property, you can also prove the converse. Yeah? So you can show that if you have a consistent embezzling family, then it will also converge to an embezzling state in the right sense. But as I said, the Van Dam and Hayden family doesn't have this property, and in that case, you can actually show, if you think of it as being defined on larger and larger spin chains, then you can actually show that it does not converge to an embezzling state, which might be a bit puzzling. What you can actually show is that if you take the Van Dam Hayden family, look at it as an algebraic state on larger and larger spin chains, converges to the trace in the end, which is semi-finite, so it doesn't have the embezzling property. But on the other hand, there's this instruction by Debbie Lung, Toner, and Watrous for like a universal embezzling object. And in that case, it's easy to show that this has this consistency property. And in that case, it even converges to universal embezzlement. So if you take that family and take the limit of the states, like sense of an algebraic state, then you get then you get the hyperfinite type 3-1 factor. In that case, out of it. Okay. Now the final example and the connection to relativistic quantum field theory, where in that setting we think of the model as basically giving us algebras of observables associated with finite regions in Minkowski space, which is here depicted by this Penrose type diagram. And all these operator algebras will again be Neumann algebras, and they come with this additional condition, that setting, which basically ensures that the theory satisfies some relativistic locality properties, that if you associate operator algebras to space-like separated regions, then these operators will commute, but usually not tensor factorized. Often you demand something like causal completeness. So if you have something going on in this region here, then the dynamical law basically tells you already what the algebra looks like in the causal completion of that region. And as I said, we also have to assume here a setting that we have Haack duality, which is in the space-time setting saying if you take the causal complement of a region, then for Neumann algebra of local observables associated with that region should be the commutant of the causal complement. And now in that setting we can consider this idealized splitting of space-time along some, say, Cauchy surface from Minkowski space, and associate these wedge-type algebras with Alice and Bob. And then it's a general result from algebraic quantum field theory that in that case these algebras will be type 3-1 algebras. So in this sense, relativistic quantum fields are universal embezzlers. And what's nice about this statement in this context is that it, on the one hand, gives an operational interpretation to the kind of infinite amount of entanglement present in the relativistic vacuum state. Typically, it is just said that the vacuum is infinitely entangled, but it's infinitely entangled in this kind of precise operational sense if you use embezzlement of entanglement to characterize it. And it also can be directly related to violation of L inequalities. So in the following sense, that if we take this CHSH coefficient with respect to this bipartition and to two wedge algebras, then we can show that since this is a standard bipartite system, that we have this bound here. So this coefficient is lower bounded in terms of this quantifier of embezzlement. And if omega is embezzling, which will be the case for the relativistic vacuum state, we actually get this maximal violation here directly. And then maybe also to comment briefly on the question about exact embezzlement, in the sense where we want to set this error here, epsilon, in this task of embezzling exactly to 0, well, then follows that in this case exact embezzling states exist if and only if this resource system is non-separable. Because I mean, we're doing this in this von Neumann algebraic setting. And basically the reason for this is that then the modular spectrum of an embezzling state, it was whole R plus, and if you would have exact embezzlement, this would mean that every value, every spectral value in the modular spectrum must be an eigenvalue. So we have an uncountable number of eigenvalues. That's why it has to be non-separable in that case. Okay, so it's the summary. So I told you about these three questions here. So whether such idealized embezzling states exist, whether we can have universal embezzlers, and in which sense universal embezzlers appear in nature or in physics. And we have seen this nice relation with the classification of von Neumann algebras and this invariance defined in terms of this embezzlement quantifier. And these were the two main examples, like spin chains and critical fermion chains for the universal embezzlement physical models. Okay. So some open problems which we have at the moment as well, since we have this kind of universal result for 1D fermion chains, at least in the free setting, it would be interesting to understand whether any critical 1D many-body system is actually universal embezzling. One could be tempted to guess this because if you're at the critical point, then typically there should be a CFT description of the large-scale properties of the physical system. And if it's a CFT, would be because of these results of algebraic quantum field theory, it would lead to type 3-1 algebras. So one would be tempted to guess that this reflects already, like in the spin chain itself, not only in the idealized large-scale structure. Then it would be interesting in which sense ground states of many-body systems or vacuum of QFT models also work as embezzling systems in a multipartite setting, where you don't have only Alice and Bob, but maybe also Eve and Charlie. And well, Lauritz will probably talk about, in his talk also, talk about how this embezzlement of entanglement relates to other forms of entanglement, like long-range entanglement and in general a large-scale structure of entanglement. So in a sense, what we mean by large-scale structure is in the, let's say, properties that only manifest if you look at very large scales and are not really dependent on local details. So if you modify the system locally, properties of entanglement are invariant under such modifications. And then some more technical questions would be, which sense can you maybe in QFT localize the operations which are necessary? So the situation I presented in quantum field theory was a bit idealized in the sense that Alice and Bob had access to this whole wedge regions in Minkowski space, but in physically it would be more sensible if you can localize it. In which sense can you do this? I mean, there are some abstract ways to do it, but they are maybe not very satisfying. And well, are there explicit ways to determine the unitaries or say something about their complexity, or what should it even mean? What complexity they have? And yeah, more technical questions would be, can we say a bit more about the range of kappa, and not only these maximal values? And is there a way that we can get away without arc duality, which is giving us a headache at the moment? Okay. Thank you.
So we started slightly late. There's maybe time for a question.
When you want to drop arc duality, did you try finite index?
Yeah, but also there we didn't see how we can. The issue is that in that case it's not so clear how we can actually go to the.
I mean, the modular flows are connected, right?
Yeah, but it's more like how to go to the monopartite. I mean, between monopartite and bipartite setting, the switch is not so clear. And just working in the monopartite setting, maybe do something.
If there's no other questions, let's thank Alexander.